And welcome back. We are going to be finishing up an example FRQ problem for an AP Physics C Mechanics course. And so this is our rotational unit. I had done part of this FRQ previously in other screencasts and explaining concepts. And now we've been able to come back and I can explain the rest of it because I've given enough background information for people to be able to understand what we're doing here. So let's read the problem. It says the hoop rod system is initially at rest and held in place but is free to rotate around its center. A constant force F is exerted tangent to the hoop for a time delta t. Derive an expression for the final angular speed of the hoop rod system. Express your answer in terms of m, l, f, delta t in physical constants as appropriate. All right, so let's think about this. So initially when you think about this, I want you to think, well, it's a force applied over a certain amount of time. Hopefully this rings a bell. Hopefully this is going to sound like an impulse to you, but even if it doesn't, we can reason it through. In other words, there are two different ways I'm going to show you how to approach part C. It depends on your style as to how you want to approach this problem. So let's go ahead and take a look at it. And so what we start with is our definition of torque. And torque has a force applied at a certain distance here. We're going to have to change this R out for one of the variables that they mention up here because we want to keep it consistent with the problem and get points and make sure that we use the same variables that they want us to use. So we're going to start with just our definition of torque, and we're also going to use something else that we know about torque. This is Newton's second law in a rotational sense. So this is like F equals ma, but the rotational version. And so we can set these two equal to each other. This is what I would call the sum of the forces strategy in a rotational sense, or you could call it the sum of the torque strategy. And what we end up with is this. And so we end up with changing out this R value for an L value, all right? And that's using the term that they have given us up here in the problem. And so I'm going to say FL is equal to I times A. Now they're talking about a force applied at a length, but over a certain amount of time. And so we need to go ahead and put that time in there. But to do that justifiably, we have to apply that delta time on both sides. Now, if you were to just look at this line right here, your immediate reaction would probably be, oh, let's just cancel out time. But I'm saying, let's leave time in for a moment, and let's leave this side alone and see what we can do with this side over here. So we know a couple things about acceleration. We know that acceleration, average angular acceleration, is going to be equal to our delta omega divided by time. And I've justified that over here. I've started with a rotational kinematics equation that we have. I noted that our initial angular speed is going to be 0. If that's the case, this is true over here. I can sub that in. And so what we end up with is going to be this. Now notice I've got a time over here, a time over here. If I cancel those out, then I end up with this equation. So this is using all equations that we have given to us on our equation sheet. It takes a little while, but it's totally doable. This is not the answer, but this is one way to get further in the problem. Now I want to show you a second pathway that you can approach this problem with. This is the translational version of impulse, and I put it in there for a reason. We're being asked about angular impulse, and I did mention that and go over that in a past screencast, but I'm going to show you by analogy what I'm talking about. It turns out that if you just have an average force, like a simple average force, and you have that force applied to an object over a certain amount of time, that is equal to a change in momentum. In other words, that is an impulse. And so this equation here can be derived from this equation up here, but it's just a simple way to think about what impulse is in a translational sense. Well, if we take that and apply it to a rotational sense, then we can say that torque times a time. So in other words, if we apply a torque over a certain amount of time, which is exactly what this problem is giving us, it's a torque applied over a certain amount of time, that is going to be equal to a change in angular momentum. And so this is the rotational version of this equation up here, and that follows up here. Now, you may not like this style of doing this problem because these circled equations in here that are circled in the orange color are not given to you, but you can use them and you can reason through this to be able to get to this point in the problem. So either path you take, either the left side or the right side, we're going to end up right here. That's not the answer, but we've gotten a lot closer to the answer for this part of the problem. And so that's what we had at the bottom of the last page. Let's continue with that. I notice that my initial angular speed is going to be 0. That means that term goes away. And I am looking for the final angular speed, so it just becomes very easy to simplify. We go ahead and substitute in our I value that we had solved for previously, and we're going to simplify what we can, and this ends up being our answer to this part of the problem. Okay, and so part D says the hoop rod system is rolling without slipping along a level horizontal surface with the angular speed found in part C at time equals 0. The system becomes rolling without slipping up a ramp as shown in the figure above. So someone has rolled this up a ramp. On the figure of the hoop rod system below, draw and label the forces, not components, that act on the system. Each force must be represented by a distinct arrow starting at and pointing away from the point at which the force is exerted on the system. These are easy points, ladies and gentlemen, but you do have to pay attention and be careful with how you do this. So you want to start the force from the point at which that force is being applied, and do not draw components ever on a free body diagram. If you have to draw out components somewhere else, do it off to the side, like not your main free body diagram drawing. All right, so let's think about our forces here. The first one that comes to mind is probably going to be gravity, right? Sometimes students get confused. They will say, well, does it matter if something is on a ramp or not? Is gravity still going to pull straight down, yes or no? And the answer is yeah, it's still going to pull straight down. Gravity doesn't care. Gravity just pulls straight down, and so that's what we have here. In any case, our gravity is going straight down. Doesn't matter if it's on a ramp or not, still goes straight down. Okay, and another force that we have to deal with, of course, is going to be the normal force. Normal force is going to be the sum of the reaction forces, you could say, that are going to be perpendicular to the surface involved. And the last one is going to be a frictional force. Now, here's the deal. Because the problem says this is rolling without slipping a couple times in the problem, it mentions it's rolling without slipping. That means this surface, as it's in contact with the triangle here, the ramp here, it's not going to slide. And if it's not sliding, we're talking about static friction. We're not talking about kinetic friction. Secondly, the big question is this going to be down the ramp or up the ramp? And that's the hard thing. Let's imagine this was like ice. How would this thing slide? And the answer is it would slide down the ramp. It would slide with kinetic friction down the ramp. Just release it from rest and have this be on ice, let's say. How would it slide? It would slide down the ramp. We know friction always points in the direction opposite that of motion or possible motion. So if this were just released on a ramp, what would happen? Well, it would slide down the ramp. So therefore, friction must be going up the ramp. And so that's what we're saying. Another way to think about this is if you think about the center of mass here in the middle versus the point of contact, and you were to just say, well, what would happen if I released it from here and it was very slippery, the surface was very slippery? Because the center of mass is to the left of the point of contact, it's going to slide to the left. And so it will pull in that direction. To oppose that, which friction always does, then friction must therefore be pointing in the upwards direction. All right, and so for part E, it says derive an expression for the change in height of the center of the hoop from the moment it reaches the bottom of the ramp until the moment it reaches its maximum height. Hopefully alarm bells are going off in your head that we're thinking that this must be a conservation of energy problem. This is something I've mentioned before, and I will mention it again. Whenever you have a change in height, like a delta H, like a change in height, hopefully that's going to be a red flag that you're dealing with a conservation of energy problem. So it says express your answer in terms of M, L, I total, omega, and physical constants as appropriate. So let's go ahead and start. We'll just say, well, our total energy to start with is equal to our total energy to end with. Sometimes you can get points for writing something out like this simple. And if we think about what form the energy we have is in, we've got rotational energy initial, we've got translational energy initial, and we've got gravitational potential energy final over here. So let's go ahead and write in those equations what we have. And what they've asked us to do, this, instead of just writing M, I wrote 4M. Why did I write 4M? We are dealing with capital M from the previous part of the problem. So the circle itself has a mass of M. Each rod has a mass of M. For a total of 4M would be our value that we would write in here. This is our equation for rotational kinetic energy. This is our equation for translational kinetic energy. Here's our equation for gravitational potential energy. All right, and at this point of the problem, oftentimes we want to bring in this equation here. This equation is special when we're dealing with these types of problems because it relates this linear velocity or speed really over here with a rotational speed or angular velocity, you could say over here. So it's relating two different aspects of it. And we want to ask yourself, all right, well, do we want to get rid of the v or do we want to get rid of the omega? And the answer is we want to get rid of the v because they're asking for the answer in terms of omega. So what I'm going to do is I'm going to go ahead and sub in for v the rotational version of this equation. So I'm going to go ahead and sub that in over here, and this is what I end up with. All I've done over here is just simplified 4/2 to 2. Next up, all I've done is I've gotten rid of the 1/2 over here by multiplying every term by 2, and so I've ended up with this. I also want to point out over here it's really important that we change this r value to L because we need to use the terms that they are using, or we will not get the point actually. So please write this in terms of what they are asking for, and in this case that's going to be a capital L. Alright, and so what I'm doing here is just isolating for h because that is what we need. And so we're starting that process and we end up with this going to this over here. And that's essentially how you would do one of these problems. So if you are able to follow along with that, take heart, you are able to do AP Physics C mechanics level material, which is an accomplishment. So good job if you're able to understand this. I'm going to be doing more screencasts on other FRQs and how to think through more of this. So if you like this video, please watch other videos that are in this series. Thank you for listening.